A telescope floating 1,000,000 miles from Earth just detected something that shouldn't exist. Two chemicals in the atmosphere of a distant planet, chemicals that on Earth are produced exclusively by living organisms. This isn't speculation or wishful thinking. It's data from the most powerful observatory humanity has ever built, pointing at a world 124 light-years away where something might be alive right now. The planet is called K2-18b. You've never heard of it, but scientists have been watching it obsessively since the James Webb Space Telescope turned its instruments toward this particular corner of the constellation Leo. What they found there has divided the scientific community into camps of cautious optimism and aggressive skepticism, because the implications are staggering. We might be looking at the first real evidence of life beyond Earth. Here's what makes this so compelling. The chemicals detected, dimethyl sulfide and dimethyl disulfide, don't just sometimes get produced by life on Earth. They're made almost exclusively by microscopic marine organisms like phytoplankton and algae. These aren't gases that form easily through random chemistry. They require specific biological processes, the kind that happen when living cells metabolize sulfur compounds in ocean water. Finding them in another planet's atmosphere is like walking into an empty house and smelling fresh coffee. Something made that. But let's pump the brakes for a second, because this story is way more complicated than the headlines suggest. K2-18b sits in what astronomers call the habitable zone of its star, a red dwarf much smaller and cooler than our Sun. The planet orbits this star every 33 days, receiving roughly the same amount of light Earth gets from the Sun. It's massive compared to our world, about 8.6 times Earth's mass and 2.6 times larger in diameter. That makes it what scientists call a sub-Neptune, somewhere between Earth and the ice giants in our own solar system. The distance? 124 light-years. That means the light the Webb telescope is analyzing left that planet during the late 1800s on Earth. We're looking at old light, ancient photons that traveled through space for more than a century before hitting Webb's mirrors and revealing their secrets. What makes K2-18b particularly interesting is that it might be what's called a Hycean world. The term was coined in 2021, a mashup of hydrogen and ocean, describing planets that weren't supposed to be habitable but might actually be perfect for life. These are worlds covered in deep oceans, potentially hundreds or even 1,000 kilometers deep in some places, with thick hydrogen-rich atmospheres above them. Before the concept of Hycean planets, scientists assumed hydrogen atmospheres would make worlds too hot for life. K2-18b is forcing a rethink of that assumption. The detection itself happened through a method called transit spectroscopy. When K2-18b passes in front of its star from our perspective, starlight filters through the planet's atmosphere before reaching us. Different molecules absorb specific wavelengths of light, creating a kind of chemical fingerprint. Webb's instruments are so sensitive they can detect these tiny variations in brightness and identify what gases are present millions of miles away. In 2023, the telescope detected methane and carbon dioxide in K2-18b's atmosphere. That was already significant, the first time such carbon-based molecules were spotted on an exoplanet in a habitable zone. But there was something else in the data, a weak signal that looked like it might be dimethyl sulfide. So the research team, led by scientists from the University of Cambridge, pointed Webb back at the planet using a different instrument, the mid-infrared instrument, designed to detect different wavelengths of light. What they found was stronger evidence for both dimethyl sulfide and dimethyl disulfide. The concentrations are wild compared to Earth. On our planet, these chemicals exist at levels below 1 part per billion in the atmosphere. On K2-18b, the estimated concentrations are over 10 parts per million. That's thousands of times stronger. If these readings are accurate, Something is pumping these gases into that atmosphere at an extraordinary rate. On Earth, the process works like this. Marine phytoplankton, particularly dinoflagellates and coccolithophores, produce a compound called DMSP as part of their cellular processes. When these organisms die or get eaten, or when viruses attack them, DMSP breaks down into dimethyl sulfide. It's a complex chain involving bacteria, enzymes, and photochemical reactions. The DMS then escapes into the atmosphere where it plays a role in cloud formation and the planet's sulfur cycle. It's a signature of biological activity in ocean ecosystems. Finding it on another world should mean something similar is happening there. Should. That's where the controversy explodes. The statistical confidence level of this detection sits at 3 sigma. In scientific terms, that means there's a 0.3% chance the signal is just random noise, a fluke in the data. Sounds pretty good, right? Except the gold standard for scientific discovery is 5 sigma, which represents a probability of less than 0.00006% that the result is random. The difference between 3 sigma and 5 sigma is the difference between interesting and definitive. The research team knows this. They've been careful not to claim they've discovered life. What they're saying is that the data they have is consistent with the presence of these biosignature molecules, and that more observations are needed. They estimate another 16 to 24 hours of observation time with Webb could push them to that 5 sigma threshold. But here's where it gets messy. Other scientists have analyzed the same data and reached different conclusions. Some argue that the DMS signal isn't actually there at all, that it overlaps too much with methane signals and the analysis methods aren't robust enough to separate them. The data, they say, is consistent with a flat line, no bump or wiggle indicating a real detection. It's a classic case of seeing what you want to see in noisy data. Then there's the magma planet hypothesis. Some researchers think K2-18b isn't a water world at all, but a hellscape with oceans of molten rock instead of liquid water. Raymond Peary-Humbert, a planetary physicist at Oxford, has run models suggesting the planet is too hot for life, that any water present would be superheated and the surface would be volcanic. If that's true, the entire Hycean world concept for K2-18b collapses. There's also the non-biological production problem. DMS has been detected on comets and in interstellar space, proving it can form without life through purely chemical processes we don't fully understand. Just because we only know biological sources on Earth doesn't mean that's the only way it forms in the universe. The cosmos is creative with chemistry in ways we're still discovering. The debate reveals something fundamental about where we are in the search for extraterrestrial life. The James Webb Space Telescope has given us capabilities we've never had before. In just a few years of operation, we've learned more about exoplanet atmospheres than in the previous 3 decades combined. But we're operating at the absolute edge of what's possible with current technology. We're trying to detect faint signals from small planets incredibly far away, and interpretation of that data requires making assumptions about alien environments we can't directly observe. This is the paradox. We finally have tools powerful enough to potentially detect life on other worlds, but we might not have tools precise enough to prove it definitively. Webb might identify the most promising candidates, the worlds worth watching more closely, but confirming life could require the next generation of telescopes that haven't been built yet. What we do know is this: K2-18b is real. It's sitting in its star's habitable zone. It has an atmosphere with carbon-based molecules. The chemistry is complex and active. Whether that chemistry includes life remains an open question, one that's driving some of the most heated scientific debates happening right now. The lead researcher, Niku Midhusudhan from Cambridge, has said that the only scenario currently explaining all the Webb data, past and present, is one where K2-18b is a Hycean world teeming with life. But he's also emphasized the need for deep skepticism, for testing and retesting, because that's how science works. No one wants to claim prematurely that we found alien life. What kind of life are we talking about if it exists? Not little green men or intelligent civilizations. The conditions on K2-18b, assuming it's habitable at all, would support microbial life at best. Think of Earth's oceans billions of years ago, filled with single-celled organisms producing gases as metabolic waste. That's the kind of biology we might be detecting, primitive but profound. The hydrogen-rich atmosphere adds another layer of complexity. Laboratory experiments show that Earth microorganisms can survive in hydrogen atmospheres, so hydrogen itself isn't a deal-breaker for life. But it changes which biosignature gases are reliable indicators. Some gases that scream life on Earth might form through non-biological processes in hydrogen-rich environments, making interpretation even trickier. The temperature is estimated between 250 and 300 Kelvin in the absence of greenhouse effects. That's cold, but not impossibly so. With the right atmospheric composition and pressure, liquid water could exist. The deeper layers of the atmosphere might be too hot, crushing, but there could be a zone, a sweet spot where conditions align. Ocean depths on Hycean worlds are staggering to contemplate. Depending on surface gravity and temperature, these oceans could extend tens to hundreds of kilometers deep, reaching pressures of 60,000 bar before the water transitions to high-pressure ice. That's an alien environment by any measure, but Earth's deep oceans host life in equally extreme conditions. Hydrothermal vents, crushing pressure, total darkness, yet life thrives. If K2-18b is producing dimethyl sulfide biologically, the implications extend far beyond one planet. Hycean worlds are thought to be common around red dwarf stars, the most numerous stars in the galaxy. Their larger sizes compared to rocky planets make them easier to observe and analyze. If these worlds can host life, the number of potentially habitable planets in the universe explodes. But we're getting ahead of ourselves. The data is preliminary, contested, requiring confirmation. The scientific process is working exactly as it should, with competing teams analyzing the same information and reaching different conclusions. That tension, that back and forth, is how we eventually arrive at truth. What happens next matters enormously. The full dataset became publicly available in late April, meaning more astronomers can now scrutinize every detail. Additional observation time with Webb has been requested. Other instruments on other telescopes might be able to contribute complementary data. The investigation is just beginning. Standing at this moment in history feels significant regardless of what we ultimately discover about K2-18b. We're asking questions about alien life not through speculation but through direct observation of another world's chemistry. We're analyzing gases in an atmosphere 124 light-years away and debating whether they come from living organisms. That alone represents a milestone. The search for life beyond Earth has entered a fundamentally new phase, one where we're no longer limited to searching for radio signals or planning distant missions to Mars. We're using infrared telescopes to sniff the air of alien worlds, looking for the chemical exhaust of biology. What we're learning is that the universe is far more complex than our models predicted, that every new observation raises new questions, and that the answer to whether we're alone might be closer than we ever imagined. But first, we need to understand what we're actually looking at. The challenge lies in how we actually detect these molecules from such an enormous distance. Light becomes the messenger. When K2-18b passes between its star and Webb's instruments, starlight filters through the planet's atmosphere. Different molecules absorb specific wavelengths, creating a unique spectral fingerprint. Each molecule has its own signature pattern, a barcode written in missing wavelengths. Webb's mid-infrared instrument was specifically designed to read these barcodes. The telescope doesn't see K2-18b directly. What it captures is the star's light after it's been altered by passing through alien air. The brightness drops slightly during transit, and that drop varies by wavelength depending on what's in the atmosphere. Methane absorbs certain infrared wavelengths. Carbon dioxide takes others. And dimethyl sulfide, if it's there, should create its own distinctive absorption pattern. The problem is that these signals are incredibly faint. We're talking about detecting changes in brightness of less than 1%, and then within that tiny signal, finding even smaller variations that indicate specific molecules. It's like trying to identify a single instrument in an orchestra from a mile away while standing next to a jet engine. The initial detection of dimethyl sulfide came from analyzing how starlight was absorbed at specific infrared wavelengths between about 3 and 5 microns. The researchers saw what they interpreted as the spectral signature of DMS, a pattern that shouldn't be there unless something is producing this molecule. But here's where it gets complicated. Dimethyl disulfide has overlapping spectral features in the same wavelength range. Both molecules belong to the same chemical family. Both are predicted biosignatures. The current data can't definitively distinguish between them. Think of it like hearing a muffled voice through a wall. You know someone's speaking, but you can't quite make out whether they said yes or yeah. Both fit what you're hearing. Additional observations might sharpen the signal enough to tell them apart, but right now, we're stuck with one or the other, possibly both. The concentrations detected make the biological interpretation even more intriguing. On Earth, dimethyl sulfide exists in the atmosphere at concentrations below 1 part per billion by volume. It's produced by marine phytoplankton, released into the air, and quickly broken down by chemical reactions. The levels are low because production is balanced by destruction. On K2-18b, the estimated concentration is over 10 parts per million, thousands of times higher than Earth's levels. That's a massive difference requiring explanation. If biology is producing DMS on K2-18b, it must be doing so at extraordinary rates, or the molecule must be more stable in that environment, or both. A hydrogen-rich atmosphere might slow down the chemical reactions that normally destroy DMS on Earth. Alternatively, if there's a vast ocean teeming with DMS-producing organisms and the atmospheric chemistry is different, concentrations could build up to levels we never see in our own atmosphere. But the skeptics have compelling counterarguments. The DMS signal isn't strong. It appears in some data analysis methods but not others. When you're working at the absolute limits of instrumental sensitivity, noise becomes a serious concern. Random fluctuations can create patterns that look like signals. Statistical tools help separate real detections from false positives, but they're not perfect, especially when the signal is weak. The 3 sigma confidence level means there's a 0.3% chance the signal is just noise, a random fluctuation that happens to look like dimethyl sulfide. That might sound pretty good, but science has a higher bar. 5 sigma confidence, the gold standard for claiming a discovery, means less than a 0.00006% chance of being wrong. We're not there yet. Not even close. Then there's the methane problem. Computer models accounting for the physics and chemistry of both DMS and methane in a hydrogen-based atmosphere suggest the signal might actually be methane, not dimethyl sulfide at all. Methane was already detected on K2-18b in previous observations. If methane absorption overlaps with where we expect to see DMS, we might be mistaking one for the other. It's like trying to hear a whisper next to someone shouting. The loud signal can mask or mimic the quiet one. Raymond Pury-Humbert from Oxford University published research suggesting K2-18b might not be a water world at all. His models indicate the planet could be too hot for liquid water oceans, that what we're seeing might be better explained by a magma planet with oceans of molten rock instead of water. If that's true, the entire Hiccean interpretation collapses. No water ocean means no marine phytoplankton-like organisms producing DMS. The whole biological hypothesis falls apart. A magma planet sounds outlandish, but it's not impossible. The temperature estimates for K2-18b range from about 250 to 300 Kelvin without greenhouse effects, but greenhouse warming from a thick hydrogen atmosphere could push surface temperatures much higher. If the deeper atmosphere is hot enough to melt rock, we're not looking at a potentially habitable world but a hellscape wrapped in hydrogen. The recent reanalysis added more fuel to the skeptical fire. Independent researchers examined the same Webb data and found that instead of a clear signal, a bump or wiggle in the spectrum, the data looks consistent with a flat line. No dimethyl sulfide. No dimethyl disulfide. Just noise and uncertainty. They argue that more observations are absolutely necessary before making any claims about biosignature gases. This is where science gets messy and beautiful at the same time. Multiple teams analyzing identical data reach different conclusions. It's not that anyone's being dishonest or incompetent. It's that interpretation at the edge of detectability involves judgment calls about data processing, statistical methods, and modeling assumptions. Different choices lead to different results. Some researchers emphasize the signal they see and argue it's worth taking seriously even if it needs confirmation. Others emphasize the uncertainty and argue the evidence doesn't meet the threshold for a credible detection. Both perspectives are valuable. The optimists push the field forward by exploring possibilities. The skeptics keep everyone honest by demanding rigorous proof. The Discovery team, led by researchers including Miku Madhusudhan, maintains that the only scenario currently explaining all the Webb data, including past and present observations, is a Hiccean world potentially hosting life. They're not claiming definitive proof. They're saying this interpretation fits the evidence better than alternatives. But they also emphasize the need for deep skepticism of their own results. Science advances through testing and retesting, not through accepting the first interesting result that comes along. What's undeniable is that we're operating at the absolute limit of current technology. Webb was designed to do exactly this kind of observation, but even Webb has constraints. The signals from small planet atmospheres are weak. The number of suitable targets is limited. The inference methods, the mathematical tools we use to extract meaning from noisy data, have inherent limitations. We're pushing against fundamental barriers of what's possible with this generation of instruments. So what comes next determines everything. The full dataset became publicly available in late April, opening the door for more astronomers to scrutinize every detail. Fresh eyes might spot something previous analyses missed. Alternative interpretations will be proposed and tested. The scientific community will collectively work through the data, and consensus will eventually emerge, though it might take months or years. Additional observation time with Webb is crucial. The team estimates that 16 to 24 hours of follow-up observations could push the statistical significance from 3 sigma to 5 sigma, crossing the threshold from intriguing possibility to credible detection. That's not a guarantee, though. More data might strengthen the signal, or it might make the whole thing disappear, revealing it was noise all along. Other instruments might contribute complementary information. Ground-based telescopes, future space missions, different observational techniques could all add pieces to the puzzle. The detection of biosignature gases isn't a one-shot deal. It's a gradual accumulation of evidence from multiple independent sources until the weight of data becomes overwhelming. But there's a deeper question lurking beneath all the technical debate. Even if we confirm dimethyl sulfide is present, even if we reach 5 sigma confidence, even if alternative explanations are ruled out, we still face the interpretation problem. Does the presence of DMS necessarily mean life? On Earth, yes. Dimethyl sulfide is produced by biological processes, mainly marine phytoplankton breaking down a precursor molecule called dimethylsulfonylpropionate. The biochemical pathways are complex, involving enzymes, bacteria, viruses, and photochemical reactions. It's deeply integrated into Earth's sulfur cycle and plays a role in cloud formation by contributing to sulfate aerosol production. The connection to life is ironclad here. But K2-18b isn't Earth. It's a world with a hydrogen atmosphere, potentially crushing pressures, temperatures, and chemistry completely unlike anything in our experience. Could there be non-biological pathways producing DMS under those exotic conditions? We genuinely don't know. DMS has been detected on comets and in the interstellar medium, proving it can form without biology in certain environments. Those detections don't involve planetary atmospheres or the concentrations we're discussing, but they demonstrate that the molecule itself isn't exclusively biological. Unknown chemistry in unknown conditions could potentially generate biosignature gases through non-living processes. This is the challenge facing astrobiology. There's no silver bullet, no single molecule that unambiguously screams life regardless of context. Everything depends on context. The molecule matters less than the environment producing it. What we need is a comprehensive understanding of what K2-18b actually is, and right now, we're operating with incomplete information. Let's step back and examine what we actually know about this world. K2-18b orbits an M-dwarf star, a red dwarf, about 124 light-years away in the constellation Leo. The star itself is smaller and cooler than our Sun, with a surface temperature around 3,457 Kelvin compared to the Sun's 5,778 Kelvin. Its radius is only 45% of the Sun's. These details matter because they shape the radiation environment, the energy budget, and the habitability prospects of any planet in the system. K2-18b completes one orbit every 33 days, placing it squarely within what astronomers call the habitable zone, the region where temperatures theoretically allow liquid water to exist on a planet's surface. It receives roughly the same amount of stellar radiation that Earth receives from the Sun. That sounds promising until you remember that habitable zone is a crude first-order approximation. It doesn't account for atmospheric composition, greenhouse effects, albedo, or a dozen other factors that determine whether a planet is genuinely habitable or a hellscape dressed in optimistic terminology. The planet is massive. 8.6 times Earth's mass. 2.6 times Earth's radius. Those numbers push it into the category of sub-Neptunes, worlds larger than Earth but smaller than Neptune. In our solar system, there's nothing quite like it. We have rocky terrestrial planets and gas giants, but nothing in between. Sub-Neptunes are common throughout the galaxy, yet we have no local example to study. That's a problem because it means we're working from theory and distant observations rather than direct knowledge. Here's where things get interesting. K2-18b's size and mass suggest it shouldn't be a rocky planet like Earth. It's too big. Traditional models predicted that planets of this size would have thick hydrogen atmospheres, crushing pressures, and no solid surface to speak of. Mini Neptunes, basically. Not places where life as we understand it could take hold. But the data from Webb complicated that picture considerably. The detection of methane and carbon dioxide in 2023 was the first hint that K2-18b might be something different. These carbon-based molecules in a habitable zone planet suggested chemistry compatible with life. Then came the potential DMS detection, and suddenly we're looking at a planet that doesn't fit neatly into existing categories. This led researchers to propose that K2-18b might be a Hycean world. The term Hycean was coined in 2021 by Niku Madhusudhan and his team at Cambridge. It's a portmanteau of hydrogen and ocean. The concept describes planets with vast liquid water oceans beneath thick hydrogen-rich atmospheres. Before this idea emerged, astronomers assumed such planets would be too hot to harbor life. The hydrogen atmosphere would trap heat through a runaway greenhouse effect, turning any water into superheated steam. But detailed modeling suggested otherwise. Under certain conditions, a hydrogen atmosphere could actually be cool enough to allow liquid water oceans at the surface. Think about what that means. A planet with an ocean covering its entire surface, potentially hundreds or even thousands of kilometers deep depending on temperature and gravity. Pressures at the ocean floor could reach 60,000 bar before transitioning to high-pressure ice phases. Above this ocean, a thick blanket of hydrogen gas, completely unlike Earth's nitrogen-oxygen atmosphere. Temperatures at the surface might reach 200 degrees Celsius or higher, yet the ocean persists because the pressure is so immense. This is not an environment remotely similar to Earth. If life exists there, it's operating under physical and chemical rules we can barely imagine. The hydrogen atmosphere alone changes everything. On Earth, certain biosignature gases are considered reliable indicators of life because they react quickly and shouldn't persist without biological replenishment. But in a hydrogen-rich atmosphere, those same gases might be produced through non-biological chemistry or might be stable enough to accumulate without life. The rulebook we've been using doesn't apply. Laboratory experiments have shown that Earth microorganisms can survive in hydrogen-rich atmospheres. Hydrogen itself isn't toxic to life. But that's different from saying life could originate and thrive in such conditions. We're extrapolating from our limited understanding of terrestrial biochemistry into a regime where we have no data. The ocean depths on a Hycean world depend critically on surface temperature and gravity. Models suggest they could span anywhere from tens of kilometers to potentially 1,000 kilometers before the pressure becomes so extreme that water transitions into exotic ice phases that exist only under crushing force. These ice layers would be hot, not cold, because temperature increases with depth. The conventional image of ice doesn't apply here. Within such an ocean, where would life exist? Near the surface, where temperatures might be survivable but radiation from the star could be intense. Deeper down, where pressure is enormous but conditions might be more stable. Around hydrothermal vents on the ocean floor, if such things exist. We genuinely don't know. The possibilities are wide open, constrained only by physics and chemistry, not by any examples we can point to. But there's a competing interpretation that throws all of this into question. Some researchers, including Raymond Peary-Humbert at Oxford, argue that K2-18b isn't a water world at all. Their models suggest it's too hot for liquid water to exist at the surface. Instead, they propose it might be a magma planet, a world where the surface is molten rock, not ocean. If that's correct, the entire Hycean hypothesis collapses, and K2-18b becomes a completely different kind of object, one with no habitability potential whatsoever. The debate hinges on details. Atmospheric composition, cloud properties, albedo, internal heat flow. Small differences in these parameters lead to radically different conclusions. One model produces a temperate water world. Another produces an inferno. Both are consistent with the limited data we have, which tells you how uncertain the situation really is. What about the concentration of DMS itself? On Earth, dimethyl sulfide exists in the atmosphere at levels below 1 part per billion by volume. Trace amounts. On K2-18b, the estimated concentration is over 10 parts per million. Thousands of times stronger. That's a massive difference. If the detection is real, it demands an explanation. Biological processes on Earth don't produce DMS at those concentrations in the atmosphere. So either K2-18b has vastly more biological activity than Earth, or the chemistry producing DMS there operates through entirely different mechanisms. Perhaps life on a Hycean world, if it exists, is incredibly productive. An ocean teeming with microorganisms, all releasing DMS as a metabolic byproduct, could potentially generate those high concentrations. Or maybe the atmospheric dynamics are different. On Earth, DMS gets oxidized quickly. On K2-18b, maybe it persists longer, accumulating to higher levels. We're speculating now, stacking assumptions on top of incomplete data. The alternative is that we're misinterpreting the signal entirely. Recent reanalyses of the Webb data suggest the DMS feature might not be there at all. Instead of a clear spectral bump indicating the molecule's presence, the data might be consistent with a flat line, just noise. The strength of the claimed detection depends entirely on how you process and interpret the raw data. Different analysis techniques produce different results. That's not ideal when you're trying to make the most important discovery in human history. Both DMS and DMDS are from the same chemical family, and their spectral features overlap in the wavelength range Webb observed. The current data can't definitively tell them apart. Future observations might resolve that ambiguity, or they might reveal that neither molecule is actually present. We're waiting on more data to settle questions that can't be answered with what we have now. The scientific process is working exactly as it should. Initial detection, public announcement, independent verification attempts, debate, more observations, gradual convergence toward truth. It's messy. It's slow. It involves false starts and dead ends. But it's the only method we have for reliably understanding reality. The alternative is wishful thinking dressed up as certainty. What happens if follow-up observations confirm DMS is really there? We're still left with the interpretation problem. Does its presence mean life, or does it mean we discovered an exotic chemical pathway that operates under conditions we've never studied? The problem runs deeper than just identifying molecules. It's about understanding what they mean in an environment nothing like Earth. When we detect DMS in our atmosphere, we know where it comes from because we've studied the organisms that produce it. We've mapped the pathways, measured the rates, understood the seasonal variations. We have context. On K2-18b, we have none of that. We're looking at a hydrogen-rich atmosphere wrapped around a planet that might be ocean, might be magma, circling a star completely different from our sun. Every assumption we make is built on Earth-based chemistry, and there's no guarantee those rules apply. Consider how DMS behaves here. Marine phytoplankton, specifically dinoflagellates and coccolithophores, synthesize it through complex biochemical pathways involving enzymes, viral interactions, and photochemical processes. Once released into the atmosphere, it oxidizes quickly, gets broken down, contributes to cloud formation. The whole cycle is tightly regulated by temperature, light availability, nutrient concentration. Change any of those parameters, and the entire system responds differently. Now imagine trying to predict what happens on a world where the atmospheric pressure is different, the radiation environment is different, the ocean chemistry is different. You can't just transplant Earth biology there and expect it to work the same way. That's why the concentration issue is so puzzling. Over 10 parts per million compared to less than 1 part per billion on Earth. If biology is producing it, the ecosystem would need to be extraordinarily productive, generating DMS at rates we've never observed. Or the atmospheric chemistry could be preventing its breakdown, allowing it to accumulate. Both scenarios require mechanisms we don't fully understand. You're trying to reverse engineer an alien biosphere from a single data point. It's like finding a footprint and trying to reconstruct the entire animal. Then there's the non-biological possibility. DMS has been detected on comets and in interstellar space, proving it can form without life. The processes aren't well understood, but they exist. Maybe K2-18b has some exotic chemistry driven by radiation, temperature gradients, or mineral interactions that produces DMS abiotically. We can't rule that out. The challenge is that we don't know all the ways molecules can form under extreme conditions. Chemistry textbooks are written based on laboratory experiments and Earth observations. We're constantly discovering that nature is more creative than our models predict. Statistical significance matters here more than in most fields. The current detection sits at 3 sigma. In particle physics, you need 5 sigma before claiming a discovery. That's because the stakes are enormous and the risk of false positives is real. 3 sigma means there's a 0.3% chance the signal is just noise, random fluctuations masquerading as a real feature. Sounds pretty good until you consider how many observations astronomers make, how many wavelengths they examine, how many molecules they search for. With enough attempts, even unlikely coincidences become probable. The researchers know this. They're calling for more observation time, specifically 16 to 24 hours with Webb, to push the detection past 5 sigma. That would reduce the false positive probability to essentially 0. But getting that telescope time isn't trivial. Webb is the most in-demand observatory in history. Every astronomer wants a piece of it. Time is allocated through competitive proposals, peer review, priority ranking. K2-18b is important, but so are hundreds of other targets. Distant galaxies, forming stars, other exoplanets. The telescope can only point in one direction at a time. Patience is required, which is frustrating when you're sitting on potentially the biggest discovery ever made. While we wait, other teams are analyzing the same data independently. That's how science progresses. Multiple groups, different analysis techniques, various assumptions. If everyone reaches the same conclusion, confidence grows. If results diverge, that tells you the signal is ambiguous and more data is essential. Recent reanalyses have been less optimistic than the original announcement. Some researchers see a flat line where others see a spectral feature. The difference comes down to data processing choices. How you remove noise, how you model the baseline, which wavelength ranges you emphasize. None of these choices are obviously right or wrong. They're judgment calls, and different judgments lead to different conclusions. This is normal in cutting-edge science, especially when working at the limits of instrumental capability. Webb is astonishingly sensitive, but it's not magic. Detecting molecules in the atmosphere of a planet 124 light-years away requires extracting incredibly faint signals from noisy data. Think about what's actually happening. Light from a distant star passes through a thin layer of gas surrounding a planet. That gas absorbs specific wavelengths corresponding to molecular vibrations. Webb measures the spectrum, looking for those absorption features. But the planet's atmosphere is tiny compared to the star. The signal you're trying to detect is a fractional change in brightness at specific wavelengths. Any instrumental artifact, any calibration error, any unaccounted variable can produce false features. The overlap between DMS and DMDS complicates things further. Both molecules are sulfur-containing organics with similar structures. Their spectral signatures overlap in the wavelength range Webb observed. You can't definitively say which one you're seeing, or if it's a combination, or if it's something else entirely producing a similar-looking feature. Future observations at different wavelengths might resolve the ambiguity, but right now, the data is consistent with multiple interpretations. What about the hydrogen-rich atmosphere itself? On Earth, biosignature gases are identified based on their behavior in our nitrogen-oxygen atmosphere. Certain molecules, like oxygen or methane in large quantities, are considered strong biosignatures because they shouldn't coexist without biology constantly replenishing them. But in a hydrogen-dominated atmosphere, those rules change. Some gases that would be biosignatures on Earth become unreliable indicators elsewhere. The chemistry is just different. Hydrogen reacts with things nitrogen doesn't. It changes oxidation states, reaction rates, equilibrium concentrations. You need entirely new models to predict what a biosignature would even look like in that environment. Microorganisms from Earth can survive in hydrogen-rich conditions. Lab experiments have demonstrated that. So hydrogen itself isn't toxic to life. But would life that evolved in a hydrogen atmosphere produce the same waste gases as Earth life? Maybe. Maybe not. Evolution is contingent. Life adapts to its environment using whatever chemistry is available. On Earth, photosynthesis uses water and produces oxygen. On a Hycean world, maybe life uses different molecules, produces different byproducts. We're looking for Earth-like biosignatures because those are the ones we know how to recognize. That doesn't mean they're the only ones that exist. The bigger question is whether we're even asking the right questions. For nearly a century, astronomers have focused on atmospheric disequilibrium as a sign of life. The idea is that certain gas mixtures shouldn't exist together unless something is actively maintaining them. Oxygen and methane, for example. They react with each other, so if you detect both in significant quantities, something must be replenishing them faster than they can react away. Life is one explanation. But it's not the only one. Geological processes, photochemistry, exotic atmospheric dynamics could also create disequilibrium. The challenge is distinguishing between biological and non-biological sources from light years away. K2-18b represents a test case for this entire approach. If the DMS detection holds up, if follow-up observations confirm it, we're forced to interpret what it means. Is it life? Is it chemistry we don't understand? Is it an instrumental artifact we haven't identified? Each answer has profound implications. If it's life, everything changes. If it's not, we've learned something important about planetary atmospheres and the limits of remote sensing. Either way, the process of figuring it out advances our understanding. The lead researchers have been careful with their language. They're not claiming definitive proof of life. They're presenting data, proposing interpretations, calling for verification. That's exactly how it should work. The temptation to overhype is enormous. This is the kind of discovery that makes careers, wins awards, gets remembered in textbooks. But claiming life prematurely, only to be proven wrong later, damages credibility and sets the field back. Better to be cautious, methodical, rigorous. Let the data accumulate. Let the debate unfold. Let the truth emerge through the messy, slow process of scientific consensus building. What happens if 5 sigma is reached and DMS is confirmed beyond doubt? We're still left with interpretation. The molecule is there, but what's producing it? That question can't be answered with spectroscopy alone. You'd need detailed atmospheric models, laboratory experiments simulating High-Cean conditions, maybe even direct detection of other biosignatures to build a coherent case. One molecule isn't enough. You need a pattern, a suite of indicators that together point toward biology as the most likely explanation. That's the standard. Anything less leaves too much room for doubt. And that's where the timeline becomes critical. The researchers estimate they need between 16 and 24 additional hours of observation time with Webb. That might not sound like much, but telescope time is precious. Webb isn't dedicated to a single target. Hundreds of research teams compete for every available hour. Scheduling those observations, collecting the data, processing it, that takes months. Maybe longer. During that waiting period, the scientific community doesn't sit idle. The original dataset became publicly available in April, which means independent researchers can now access the same raw data. They'll run their own analyses, apply different statistical methods, test alternative interpretations. Some will support the findings. Others will challenge them. That's the messy reality of frontier science. Consensus doesn't emerge from a single paper but from a community-wide process of scrutiny and verification. Here's what makes this particularly complicated. The signal isn't clean. It's buried in noise, overlapping with methane spectral features, sitting right at the edge of what current instruments can reliably detect. Different teams using different data reduction techniques might reach different conclusions about whether the bump in the spectrum is real or an artifact. That's already happening. Recent reanalyses of the same data suggest the signal might be consistent with a flat line, no feature at all. The original team stands by their results, pointing to specific wavelengths and modeling approaches that support the detection. Who's right? More data will tell. But even if the 5 sigma threshold is eventually reached, even if DMS is confirmed with statistical certainty, we're not done. Confirmation means the molecule is there. It doesn't automatically mean life put it there. You'd still need to rule out non-biological explanations. And here's where it gets tricky. DMS has been detected in comets. It's been found in the interstellar medium, the diffuse gas and dust between stars. That proves it can form through purely chemical processes, no biology required. So how do you distinguish between biological and non-biological sources from 124 light-years away? Context matters. On Earth, DMS concentrations in the atmosphere are typically below 1 part per billion. On K2-18b, the estimated concentration is over 10 parts per million, thousands of times higher. That difference is significant. Non-biological processes tend to produce trace amounts, not massive concentrations. But that's an assumption based on Earth chemistry. Maybe High-Cean world chemistry operates differently. Maybe there's some exotic photochemical pathway we haven't considered that churns out DMS at high concentrations without biology. You can't rule it out just because we haven't thought of it yet. This is why the search for biosignatures requires multiple lines of evidence. One molecule, however compelling, isn't enough. You need a pattern. a suite of gases that together make biological production the most parsimonious explanation. The researchers detected methane and carbon dioxide in earlier observations. Those are consistent with biological activity, but they're also produced by geological processes. Add DMS to the mix and the biological hypothesis becomes stronger. But it's still not definitive. You'd want to see other sulfur compounds, maybe organic molecules, signatures of metabolic waste products that don't have obvious non-biological sources. The challenge is that we're working with incredibly limited information. Transmission spectroscopy gives you atmospheric composition, nothing more. You can't see the surface. You can't measure ocean salinity or pH. You can't detect cellular structures or DNA. All you have is the chemical fingerprint of gases backlit by starlight. From that, you're trying to infer the presence of life. It's like trying to diagnose a patient's illness by analyzing their breath, except the patient is 124 light-years away and you only get to sample their breath once every few years. What would make the case stronger? Detection of gases that have no known non-biological source. On Earth, certain compounds are produced exclusively by life. Methyl chloride, for example, is made by marine algae and has no significant geological source. If you detected that on K2-18b, alongside DMS and other biosignatures, the biological hypothesis would become much harder to dismiss. But even then, you'd need to demonstrate that no unknown chemistry could produce those gases. That's a high bar. Some researchers argue we're approaching this wrong. Instead of looking for individual molecules, we should be looking for chemical disequilibrium patterns that only life can sustain. The idea is that life constantly pushes chemistry away from equilibrium, maintaining gas mixtures that would otherwise react away. On Earth, oxygen and methane coexist because life produces both faster than they can react with each other. Without life, that disequilibrium would collapse within a few million years. If you can demonstrate that K2-18b's atmosphere is in persistent disequilibrium and that no geological or photochemical process can maintain it, that's stronger evidence than any single molecule. The problem is proving the negative. How do you demonstrate that no unknown process exists? You can't. You can only show that all known processes fail to explain the data. That's weaker than it sounds because planetary science is full of surprises. Venus has phosphine in its atmosphere, and nobody's entirely sure why. It could be life, or it could be some weird atmospheric chemistry we don't understand yet. The same uncertainty applies here. There's also the question of what kind of life we're talking about. If K2-18b hosts biology, it's almost certainly microbial. Single-celled organisms living in the ocean, metabolizing whatever chemistry is available. Not fish, not plants, nothing complex. The conditions wouldn't support it. High atmospheric pressure, crushing ocean depths, temperatures that might reach 200 degrees Celsius in deeper layers. Surface waters might be cooler, more temperate, but you're still looking at an alien environment fundamentally different from Earth. Life adapted to that environment wouldn't look like Earth life. It would be something else entirely. Which raises an interesting philosophical point. When we search for biosignatures, we're inherently biased toward Earth-like life because that's the only reference we have. We know what Earth life produces, what gases it releases, what chemical disequilibria it creates. But life elsewhere might operate on completely different principles. Silicon-based instead of carbon-based. Using ammonia instead of water. Metabolizing in ways we haven't imagined. If that's the case, we might be looking right at biosignatures without recognizing them because they don't match our preconceptions. This is the central tension in astrobiology. You want to cast a wide net, consider all possibilities, but you also need specific, testable predictions. You can't search for everything simultaneously. You have to prioritize, make educated guesses about what's most likely. That inevitably introduces bias. The challenge is being aware of that bias and not letting it blind you to unexpected findings. K2-18b might not be the planet where we finally confirm extraterrestrial life. The signal might not hold up. The interpretation might shift as more data comes in. But it's pushing the field forward regardless. It's forcing researchers to refine their models, develop better detection methods, think harder about what constitutes convincing evidence. Each attempt, whether successful or not, teaches us something about planetary atmospheres, about the limits of our instruments, about the complexity of distinguishing biology from chemistry. The next generation of telescopes will help. Instruments currently being designed will have higher sensitivity, better spectral resolution, the ability to study smaller, rockier planets. They'll be able to detect fainter signals, resolve overlapping spectral features, measure atmospheric composition with greater precision. That will narrow the uncertainty, make the interpretations less ambiguous. But it won't eliminate the fundamental challenge. We're still doing remote sensing across vast distances, inferring complex phenomena from limited data. What happens if we do eventually confirm life on K2-18b or another exoplanet? The implications extend far beyond astronomy. It would reshape our understanding of biology, showing that life isn't unique to Earth but emerges wherever conditions allow. It would raise questions about how common life is, whether intelligence is inevitable, what our place is in a universe teeming with biology. Those aren't just scientific questions. They're philosophical, even existential. But we're not there yet. Right now, we're in the uncertain middle ground between detection and confirmation. The data is suggestive but not conclusive. The interpretations are plausible but not proven. The path forward requires patience, rigor, and a willingness to accept that we might not get definitive answers as quickly as we'd like. The scientific process doesn't move in straight lines. It advances through incremental steps, occasional breakthroughs, and frequent setbacks. Each observation adds a data point, constrains the possibilities, eliminates hypotheses that don't fit. That's how knowledge builds. Not through sudden revelations, but through accumulated evidence slowly shifting the balance of probability. K2-18b represents one data point in that larger process. A significant one, certainly. The detection of potential biosignature gases on a habitable zone planet using our most advanced telescope is noteworthy regardless of how the interpretation ultimately resolves. But it's still just one planet among thousands we've discovered, millions that likely exist in our galaxy alone. Consider the broader landscape. Webb has only been operational since 2022. In that short time, it's already transformed exoplanet science, providing atmospheric data that was impossible to obtain before. JWST-39b, a hot Jupiter, revealed a complete chemical inventory including water vapor, carbon dioxide, carbon monoxide, sodium, potassium, and sulfur dioxide. That last one was particularly interesting because it requires photochemistry, chemical reactions driven by starlight in the upper atmosphere. It showed that planets far different from Earth still have complex atmospheric processes. TOI-561b, an ultra-hot super-Earth, challenged assumptions about small planets close to their stars. Conventional wisdom said they shouldn't retain atmospheres. The stellar radiation should strip away any gases. Yet Webb detected what appears to be a thick atmosphere, possibly above a global magma ocean. the planet's unusually low density suddenly made sense. It's not just rock. It has a substantial gaseous envelope despite the harsh environment. These discoveries matter because they expand our understanding of what's possible. Each unexpected finding forces researchers to reconsider their models, question their assumptions, think more creatively about planetary formation and evolution. That's the value of exploration. Not just confirming what you already believe, but discovering what you didn't anticipate. Which brings us back to the central question. How do we know when we've actually found life? The answer isn't simple because life itself isn't simple. On Earth, biology produces countless chemical signatures. Oxygen, methane, phosphine, nitrous oxide, dimethyl sulfide, hundreds of volatile organic compounds. But almost all of these can also be produced through non-biological processes under the right conditions. Oxygen comes from photosynthesis, but also from water vapor breaking apart in the upper atmosphere. Methane comes from microbes, but also from volcanic activity and geochemical reactions. Phosphine might come from life, but it's also produced in gas giants through atmospheric chemistry. The challenge is distinguishing biological production from geological or atmospheric production when you can't visit the planet to investigate directly. You're limited to remote observations, spectral analysis, statistical inference. That means looking for combinations of gases that are unlikely to coexist without biology. On Earth, oxygen and methane together create a disequilibrium signature. They react with each other chemically, so their simultaneous presence suggests continuous replenishment from different sources. Biology maintains that disequilibrium. Remove life, and the gases would equilibrate, disappearing over geological timescales. But what if alien biochemistry operates differently? What if life elsewhere uses different metabolic pathways, produces different waste products, creates different atmospheric signatures? We wouldn't necessarily recognize it because we're calibrated to Earth's patterns. This is the biosignature detection paradox. You need specific predictions to guide your search, but those predictions inevitably narrow your perspective. You might miss what you're not looking for. Some researchers argue for a more agnostic approach. Instead of searching for specific molecules, look for any chemical disequilibrium that can't be explained by known planetary processes. If you detect an atmosphere that's thermodynamically unstable, something must be maintaining it. That something could be biology. The problem with this approach is that planetary processes are complex and not fully understood. What looks like unexplained disequilibrium might just be physics we haven't modeled correctly. You risk false positives if you're not careful. The flip side is false negatives. If you're too conservative, demanding ironclad proof before accepting a biosignature, you might dismiss genuine detections because they don't fit your preconceptions. Science requires balancing these risks. Being open to unexpected findings while maintaining rigorous standards of evidence. It's not easy. The history of science is littered with premature announcements, overinterpreted data, claims that didn't hold up to scrutiny. That's why the K2-18b team is proceeding cautiously despite the suggestive signals. They've reached 3 sigma statistical significance, meaning there's a 0.3% chance the signal is random noise. That sounds compelling, but in scientific terms, it's not enough for confirmation. The standard for discovery claims is 5 sigma, which corresponds to a probability of less than 0.00006% that the signal is coincidental. Getting from 3 sigma to 5 sigma requires more observation time, better data, additional wavelength coverage. The team estimates they need 16 to 24 more hours of telescope time to reach that threshold. Whether they'll get it is uncertain. Telescope time is precious. Webb is oversubscribed by a factor of 10, meaning far more proposals than available observation slots. Every hour spent on K2-18b is an hour not spent on other targets. Committees evaluate proposals, prioritize based on scientific merit, feasibility, likely impact. K2-18b is compelling, but so are dozens of other candidates. The allocation process is competitive. Assuming they do get the time and the signal strengthens to 5 sigma, then what? Even definitive detection of dimethyl sulfide doesn't automatically mean life. It just means biology becomes the most likely explanation. You'd still need to rule out alternative scenarios. Could photochemistry in a hydrogen-rich atmosphere produce DMS through pathways we haven't considered? Could geological processes release sulfur compounds that combine in the atmosphere to form DMS? Are there reactions involving minerals, water, and atmospheric gases that might generate these molecules without biology? These questions need answers before claiming discovery. The scientific community would scrutinize every aspect. The data reduction methods, the spectral analysis techniques, the atmospheric models, the statistical treatments. Other teams would attempt independent analyses using the same data. They'd look for errors, biases, alternative interpretations. This process is essential. Extraordinary claims require extraordinary evidence, and the claim of extraterrestrial life is about as extraordinary as it gets. The evidence needs to withstand intense scrutiny from multiple independent groups before acceptance. Even if the biosignature interpretation holds up, you're still left with profound uncertainties. You know life probably exists on that planet, but you don't know what kind. You don't know how it originated, how it evolved, whether it's widespread or rare. You don't know if it's simple or complex, ancient or recent, thriving or barely surviving. All you have is a chemical signature in an atmosphere 124 light-years away. The rest is inference and speculation. That might seem frustrating, but it's actually remarkable. A century ago, we didn't know if other planets existed beyond our solar system. 50 years ago, we had no way to study their atmospheres. 20 years ago, we couldn't detect biosignature gases even if they were present. Now we're at the threshold of potentially confirming life elsewhere. The pace of progress has been extraordinary. The capabilities we've developed in just a few decades would have seemed like science fiction to earlier generations. Future telescopes will push further. The Habitable Worlds Observatory, currently in early planning stages, is designed specifically to characterize Earth-like planets around Sun-like stars. It will have a coronagraph to block starlight, allowing direct imaging of planets in reflected light rather than relying on transit spectroscopy. That opens up new possibilities. You could study planets that don't happen to pass in front of their stars from our perspective. You could analyze surface features, detect seasonal variations, maybe even observe geological activity. Ground-based extremely large telescopes coming online in the next decade will complement space-based observations. The 30-meter telescope, the Giant Magellan Telescope, and the Extremely Large Telescope will have collecting areas far larger than Webb, allowing them to gather more photons and achieve higher spectral resolution. They'll be limited by Earth's atmosphere, but adaptive optic systems are becoming sophisticated enough to compensate. Combined with space telescopes, they'll provide multiple independent measurements of planetary atmospheres, reducing uncertainties and strengthening conclusions. The technology is advancing rapidly. So is our theoretical understanding. Researchers are developing more sophisticated atmospheric models, accounting for complex chemistry, cloud formation, atmospheric circulation patterns. They're studying extreme environments on Earth, places where life persists under conditions previously thought uninhabitable. Deep ocean vents, acidic hot springs, Antarctic ice, high-altitude deserts. Each discovery of terrestrial extremophiles expands the envelope of possibility for where life might exist elsewhere. This is the context in which K2-18b should be understood. Not as a definitive answer, but as a milestone in an ongoing journey. We're learning how to ask the right questions, developing the tools to answer them, building the knowledge base to interpret what we find. Each planet we study teaches us something new about atmospheric processes, planetary formation, the conditions necessary for habitability. That knowledge accumulates, refining our search strategies and improving our detection capabilities. The question of whether we're alone in the universe won't be answered by a single observation. It will be answered through accumulated evidence from multiple planets, multiple biosignatures, multiple independent confirmation. K2-18b might be part of that answer. Or it might turn out to be a false alarm, teaching us about atmospheric chemistry instead of biology. Either way, it's moving the field forward. That's what matters. Not whether this particular planet hosts life, but whether we're getting better at finding out. And we are. The tools exist now. The methods are proven. The candidates are identified. What happens next depends on how we use them. The timeline stretches ahead with uncomfortable uncertainty. Those additional observation hours with Webb might happen next year. Or the year after. Scheduling depends on committee decisions, competing priorities, telescope availability. Meanwhile, K2-18b keeps orbiting its red dwarf star, oblivious to our scrutiny, its atmosphere continuing whatever processes are producing those spectral features we're arguing about. What's clear is that we've crossed a threshold. Not necessarily the threshold of discovering life, but the threshold of being able to look. Webb represents a capability that didn't exist 5 years ago. We can now analyze the atmospheric composition of planets in habitable zones around other stars. That's not incremental progress. That's a fundamental shift in what's possible. Think about where we were just a generation ago. The first exoplanet around a sun-like star was confirmed in 1995. Before that, we literally didn't know if planets existed beyond our solar system. We suspected they did, but suspicion isn't knowledge. Now we've cataloged thousands. We know that planets are common, that rocky worlds exist throughout the galaxy, that many orbit within their stars' habitable zones. The question has shifted from, are there other worlds? To, what are those worlds like? K2-18b forces us to confront how we answer that second question. The data is ambiguous. The interpretations diverge. But the fact that we're having this debate at all, arguing over spectral features in the atmosphere of a planet 124 light-years away, that's the real story. We're not just theorizing anymore. We're measuring, analyzing, testing hypotheses against actual observations. Whether dimethyl sulfide is really there, whether it's produced by life or exotic chemistry, those questions will get resolved through the normal scientific process. More data will arrive. Better models will be developed. Consensus will eventually form, though it might take years. That's fine. Science doesn't run on news cycle timelines. It runs on evidence accumulation, and evidence takes time. The broader trajectory is what matters. Each planet studied adds to our understanding of atmospheric processes, of what's normal and what's anomalous, of how to distinguish biology from geology from instrumental artifacts. We're building a reference library of planetary atmospheres, learning to read chemical signatures across an enormous range of conditions. That knowledge base will prove invaluable when the next candidate emerges, and the one after that. Because K2-18b won't be the last world where we detect potential biosignatures. Webb is just getting started. There are thousands of exoplanets within its observational range. Sun will be too hot, too cold, too massive, too small. But Sun will sit in that narrow band of conditions where life as we understand it might exist. Those are the targets. Those are where humanity's attention will focus over the coming decades. The search for life beyond Earth isn't a single moment of discovery. It's a process of gradually narrowing uncertainty, eliminating alternatives, building confidence through accumulated evidence. Maybe K2-18b is the first confirmed detection. Maybe it's a stepping stone toward understanding Hycean worlds that don't actually host life. Maybe it's teaching us that our biosignature detection methods need refinement before we can trust them. All of those outcomes advance the field. What we're witnessing is the maturation of a scientific discipline. Astrobiology is transitioning from speculation to observation, from hypothetical arguments to data-driven conclusions. The tools exist now to test ideas that were purely theoretical a decade ago. That's transformative. It changes the conversation from, could there be life? To, here's what we measured, here's what it might mean, here's how we find out for sure. The philosophical implications lurk beneath the technical debates. If life exists on K2-18b, even simple microbial life, it would demonstrate that biology isn't unique to Earth. It would show that the chemical and physical conditions necessary for life arise naturally when planets form in habitable zones. That has profound consequences for how common life might be throughout the galaxy, throughout the universe. If it happened twice in one small corner of space, it's probably happened billions of times elsewhere. But those implications only matter if the detection is real. And that's still uncertain. The data is suggestive. The interpretation is plausible. The statistical confidence is approaching significance. But we're not there yet. The gap between intriguing possibility and confirmed discovery remains, and crossing that gap requires rigor that can't be rushed. So we wait. For more telescope time. For additional observations. For independent verification. For the slow grinding process of science to either confirm or refute what the initial data suggested. That waiting is hard, especially when you're potentially sitting on the biggest discovery in human history. But it's necessary. Getting it right matters more than getting it first. Meanwhile, the search continues. Other planets. Other biosignatures. Other research teams developing new detection methods, new analytical techniques, new ways of interpreting atmospheric chemistry. The field is advancing on multiple fronts simultaneously. K2-18b is one thread in a much larger tapestry. Whether this particular thread leads to confirmation of life or not, the tapestry keeps growing, the picture keeps coming into focus. What happens over the next few years will determine whether K2-18b enters the history books as the first world where we found evidence of extraterrestrial life, or as a cautionary tale about the challenges of biosignature detection. Either way, it's already changed how we think about the search. It's demonstrated that we have the capability to detect potential biosignatures. It's revealed the complexity of interpretation. It's shown us both the promise and the pitfalls of this endeavor. The universe doesn't care about our timelines or our eagerness for answers. It will reveal its secrets at its own pace, through careful observation and rigorous analysis. Our job is to keep looking, keep measuring, keep questioning our interpretations until the weight of evidence becomes overwhelming. That's how we'll eventually answer the question of whether we're alone. Not through a single dramatic discovery, but through accumulated knowledge that makes the answer undeniable. K2-18b might be that answer. Or it might be a false start. The only way to know is to keep looking at the data, keep refining the models, keep pushing the instruments to their limits. Because somewhere out there, on some planet around some distant star, life probably exists. Finding it, proving it, understanding it, that's the challenge defining this era of astronomy. And we're closer now than we've ever been.